Welcome to Unit 2, Lesson 6, Graphing Quadratic Relations Given Any Form. So last year, you would have spent a lot of time working with quadratic relations, and one of the most important skills that you worked on was graphing those relations. And the first form that you would have learned that a quadratic relation could be written in is this thing called vertex form, because that's actually the easiest form to use for graphing purposes. But as your lessons went on, you would have also learned about other forms that these quadratic relations could take, such as factored form and standard form. And there are some techniques we can use to graph from those forms as well. So we're going to review each of those. But we're going to go in the same order that you likely would have learned these things last year. So the first one, as I said, and the most important one for graphing is vertex form. So a vertex form of a quadratic relation gets its name because when we write it in this way, these values h and k specifically tell us the actual vertex point. Now just be careful when you look at the h value. The h value, notice, is being subtracted inside the bracket with the x. So essentially we have to look for any number that's being subtracted with the bracket with the x inside that bracket will be our h value. And that makes it the x-coordinate of our vertex. Whatever k is, any extra number that's sort of hanging off the end, either added or subtracted, tells us what the y-coordinate of our vertex is. And that gives us a starting point. That's essential for us to be able to graph this. From there, though, there's this other really important piece, the a value. And the a value actually tells us two different things. The first part of it is whether or not it's positive or negative. And that tells us something important. Well, if it's a positive value, it means that the whole parabola shape, remember parabola is just the shape, that sort of U-shaped pattern that a quadratic relation takes. And if a is greater than 0, that entire parabola points up, and that means the vertex point is its minimum or its lowest possible y value. If the a value is negative, in other words, less than 0, then the whole parabola points downwards, and that means the vertex is actually at the highest or maximum possible y value that you would see. But the a value also tells us a lot about the shape of the parabola. So what this little piece here is representing, those two straight lines on either side of a, just mean absolute value. Or in other words, ignoring any negative signs. So if your a value is, for example, -2, the absolute value of that is just the 2. So what this is saying is we just care right now about what is the actual number value of your a. So is it something like a 2 or a 3, or maybe something like a fraction, like 1/2 or 1/3? Well, that's going to tell us whether or not the parabola has been expanded, for example, if it was a 2 or a 3, or if it's been sort of compressed or squashed down, like if it was a 1/2 or a 1/3. And so, because that's all about the shape of the parabola, we use this word congruent. Just like in elementary school, when you talked about two shapes that were the same as one another, we would say those shapes are congruent. And so what we're saying here is that, for example, anything, let's say, that has an a value of 2 in front of it, they are all going to be congruent to something like y equals 2x squared. So in other words, it will have the same shape. Maybe it'll point up, maybe it'll point down, but if it has an a value that has a 2 in it, whether it's positive or negative, it's going to be congruent or have the same shape as the basic parabola y equals 2x squared. That's sort of the idea there. So this will, of course, make more sense as we see some examples. So we're going to go through first with each of these examples and break down some of the key information that it's asking for here in this question. And of course, the reason for that is that all of that key information is going to give us the tools that we need to graph this thing out. So first off, we need to find the h and k values from this first equation that we're working with in order to find the vertex. But remember, h is whatever value is being subtracted inside the bracket with the x. But if we take a look at our bracket right now, we actually don't see anything subtracted. We see a 2 being added. But remember, a different way we could think of this bracket, and you don't have to actually write this down, but you can think of this as x subtract -2 all squared. And so really what that means is that when you see a plus inside of the bracket, your h value is actually just the opposite sign. Your h value will be negative in that case. So our h value is -2. And then your k value is a little more simple and direct. It's just exactly whatever number is tacked onto the end. And in this case, because it's a subtraction of 4 in our original relation, that just means -4 is the actual value we want. Then we need to decide which way does this thing open. Well, that's got to do a lot with our a value. And if we don't see an a value, then we just need to imagine that it's really just a +1. And so if we have a +1, what that's telling us is that it's got to open up. It's a positive. Not only is it positive, but it's just a 1. So it's going to be congruent to any other basic parabola shape that has an a value of 1. Or in other words, it's going to be congruent or the same shape as just actually the most basic parabola you could draw, which is y = x². And then this next blank we have about the value part is asking, really, is this a minimum value that it's going to have or a maximum value? So remember, if this thing points upwards, then that vertex point is the lowest y value that we would see. So it's got a minimum value. And when we say the minimum or maximum value, we mean how high or low on the y-axis does it go. So what's that y value? So it's really the y value of our vertex, but then we often ask, when does that minimum or maximum value occur? So in this case, the minimum occurs when the x value is -2. So that gives us some really important essential information to work with. And then we just need to think about how we're going to graph from the vertex, because we obviously have a single starting point. That's why we found the vertex first. But then we need to follow a certain pattern to build up all of our points from there. So here's the pattern that you could use. So from the vertex, and this is important to remind yourself, and so I'm just writing this down to remind yourself, every time we run through this pattern, we stop and we restart from the vertex each time. So I start from my vertex and I go over by 1 unit, either to the left or the right. Usually I tend to make my first branch towards the right, and then I just do a symmetrical one towards the left, but you can start by going over in either direction. So we go over by 1, and then we go up by 1 squared. So we're going to be going up each time by the square of whatever we went over by. So the next one will go 2 over and 2 squared, or in other words, 4 units up. Then for our next point, we can go 3 over, and you guessed it, oops, it'll be 3 squared, which is 9 units up. And again, we just start from the vertex point, -2 and -4. So this first one I actually am going to go through and sort of walk you through that process fully. The other ones I'm just going to sort of get you started and let you try and do those independently and check them after. But for this one, let's just go through it together. So we start at -2 and -4, so that would be down right about here. And then we go, I'm going to make my branch over to the right, so I go over by 1 and up by 1, back to my vertex, then over by 2 and up by 4, then back to my vertex, over by 3 and up by 9. And now I can restate that entire pattern and do it all to the left, or I can just use a little bit of the symmetry that I know to just draw points at the same height or same sort of vertical level as the one directly across from them, across the line of symmetry. So I have one there, I have one there, and I have one there. And again, if you just need to count out that pattern again, you can do that as well. Once I put all of that together, connect them with a roughly smooth curve, if you can, as smooth of a curve as you can make, and make sure that each branch has an arrow at the end of it to indicate that it would continue on in that same direction. And you don't need to label too much about this, but it is always really important to label the most important point on every parabola, which is its vertex point. So I do want to see you get in the habit of just labeling its vertex because it's such an important point for it. Okay, let's try another example. So, for this one here, now we actually do see, if we take a look at our bracket with the x, we actually do see a value being subtracted already. So that directly is telling us our h value, or the x-coordinate of our vertex. So if 5 is being subtracted in the bracket, then 5 is our h value. And we see that we have a k value of 1. Positive 1 is being tacked on to the end of that relation. And then we look at the a value. And it's a -3. So that -3 is telling us two things. The negative is telling us that it opens down. And the 3 part tells us that it's going to be congruent to, or the same shape as, anything that has a 3 as its a value, whether it's a +3 or a -3. So it's going to be, and I should say 3x squared. So the difference here is that instead of following the most basic parabola shape like this one did, this is literally the most basic parabola shape, is y equals x squared. And that's what our previous one just followed, except it was located in a different spot. Now, it's not going to be the simplest possible parabola shape, but it's going to be that basic parabola shape that's being then expanded or stretched out 3 times longer and skinnier than it was before. It's going to be congruent to, or the same shape as that. In this case, then, we have to ask, is it a maximum or a minimum? Well, if the whole thing points down, then its vertex occurs at its highest or maximum point. And that y value when that occurs is a y value of 1, and it occurs when x is equal to 5. So now, in a moment, I am going to give you time to try this independently, but we should talk about how the pattern's going to be different now. So once again, of course, we do start from the vertex. But now when we go 1 unit over, instead of going 1 squared unit up, we need to deal with this fact that we're now congruent to 3x squared. It's this idea that we're now expanding things out, so it's going to jump up 3 times higher than it did if it was just an x squared. So what does that mean? Well, instead of doing just 1 squared units up, or sorry, I guess that should be down, because we are going down, but instead of just doing 1 squared units down, we're going to do 3 times that. Then we'll go 2 units over, and instead of just going 2 squared units down, you guessed it, we're going to go 3 times 2 squared, which is really like going 12 units down. And then if we have room for it, when we go 3 over, again, instead of just going 3 squared units down, we're going to go 3 times 3 squared units down. So these extra 3 times bits that I added into our new pattern is what's going to allow this to actually stretch out and jump downwards 3 times quicker than the more basic parabola shape actually would. Pause the video now at this stage, take some time and try and plot this out either on the grid that you have if you have the printed note, or on a separate sheet of graph paper, and then restart the video to take a look at how mine went and compare. So here is the resulting graph that I ended up with, and a couple things we can make note of. Notice that from my vertex point, my next 2 points did go, instead of just 1 unit down each, they went 3 units down. And then for my next points, I had to go 12 units down from my vertex, so I just barely fit those in down there. And then this may happen to you in a lot of cases, especially when you have a fairly large expansion factor, like 3 there. You might not be able to fit any more points than that. So at a bare minimum, though, to be able to draw a good sketch, you should have at least 5 points like we have here. So that means the original vertex point and at least 2 points on each of your branches is a good way to have a pretty accurate sketch, and that's about as accurate as we need to get in this case. Now, we know that vertex form, as I mentioned off the start, is not the only way that we see quadratic relations. In fact, you've already seen earlier in this unit that quadratics can take on many different forms, whether it's a relation or an equation. And one of the very important forms that you also learned last year, because you spent so much time learning about factoring, was the factored form of a quadratic relation. And it didn't directly tell you the vertex, but there are some ways we can use some of the information it does give you to figure out what the vertex is. So first off, just a little review of factored form. It looks just like this, of course, and it's got two new values we need to introduce as part of it. So here we have two separate factors that it's been broken into, and each factor, if it has a specific number being subtracted in each bracket, we call those numbers R and S. And those numbers being subtracted in each bracket then, those R and S values are actually our x-intercepts. So we have this thing to notice once again that inside these brackets, it is a minus. So if we ever see a plus inside one of our factors, then the R and the S values are just going to have the opposite sign to what we see inside that bracket. Now, we also can make note of this idea that these x-intercepts can help us to find the vertex. So if I just do a very quick rough sketch of a parabola, something like this, we know that it's going to have two x-intercepts, like so, that cross the x-axis there. What we're trying to find, though, is this vertex point and where it's located. But we know that its x-coordinate is going to line up with this spot on the x-axis, which, if we look, is an equal distance from each of our two x-intercepts. Another way to say this is that the x-coordinate of our vertex, which is sort of like our h value, so you can actually sort of remind yourself this is really like an h value we're looking for, that is the midpoint exactly in between your two x-intercepts. And a quick way that we can find the midpoint in between two values, you might have learned this in grade 10, depending on where you're coming from, is to add the two values together and divide by 2. It's like we're actually taking the average of the two values. Add them together and divide by 2. And then once we find that h value, we can sub it into this original equation to find the y value of our vertex, or the k value is what we would often call that as well. But the a value, we also have an a value, and nice thing is it means the exact same thing that it meant in vertex form. Whether it's positive or negative tells us if it's a minimum or a maximum respectively, and the actual number value of it tells us how much the parabola is going to be either expanded out or compressed down. So we'll have to do a little bit of extra work on these, but let's take a look at what we're going to do. We're going to try and list off a lot of the same important information and then do some graphing. So here we can right away actually just state its x-intercepts, and notice that both of the brackets already have a subtraction happening inside of them. So that means the numbers that we see directly being subtracted would be our x-intercepts. In this case, that would be 3 and 7. So the vertex, we can't write anything on that line just yet until we do a little bit of work first. So we'd say the x-coordinate of our vertex is going to be equal to what we get when we do 3 plus 7, and then divide it by 2. In other words, we're trying to find the number that is right between 3 and 7. Now, you might be able to actually just work that out in your head, but you'll be able to verify it by doing this quick calculation. Of course, it's 10 over 2, or in other words, it's 5. And so now that becomes the x-coordinate of our vertex, and we can find the y value that goes with it just the same way we could always find a y that goes with an x by substituting in. So we take our original equation and we replace everywhere that we see x with a 5. And 5 minus 7. And so y is really equal to 2 times positive 2 times negative 2. We multiply all of that together, we get negative 8. So therefore we put all of that together, and we have the vertex 5, negative 8. So it took us a little bit of work. It will take those two little steps, but keep in mind now that when we have the x-intercepts from factored form, we can fairly easily still find its vertex. And that's going to give us a starting point and allow us to graph much easier. We can now also make note of this fact that the a value is positive and it's a 2. So that means it's going to open up because it's positive, and because it's a 2, it's going to be congruent to, it's going to have the same shape as any parabola that has a 2 as its a value. So it's going to follow the same shape as the most basic thing that has a 2 as its a value, which is y equals 2x squared. Because it points up, it has a minimum value. And that minimum value is its y value of its vertex, which we worked out was -8. And we also worked out that it occurs when the y value, or when the x value is equal to 5, excuse me. So once again, now using all of this information that we've put together, so really the most important things for graphing are to make note of the vertex that we're starting from, the fact that it opens up, and now the fact that it's going to expand by a factor of 2 in the way that it will jump up twice as much with each x value that we go over by. So take some time now, graph this yourself, and pause the video at this stage, and then restart it to see what mine looks like. So here's how mine ended up looking, so you can compare. Once again, make sure we're labeling our vertex. And you can see I just barely was able to fit those 2 additional points. So we even actually fit 7 points on this grid, just barely. So we were able to fit that. If you can't, again, at least a minimum of 5 points is still a very accurate sketch. But in this case, because we had the grid space, we could add those extra 2 top ones as well. Let's try another one. So this one here, we can definitely see that it is in factored form, but it looks a little bit different than the other factored form. We definitely see one factor that's in a bracket here, but then we see just an x. So it's important to remember that we could think of that as being its own little bracket. So we could easily make a bracket, x plus 0, that equals the exact same thing as just x. But suddenly if we make a bracket that's x plus 0, then we can clearly see what the other x-intercept is. So one of the x-intercepts comes from this bracket, and it's the -4. So we can write that one down. One of our x-intercepts is -4, and the other one is just 0 itself. So if we want to find our vertex, we find the x-coordinate of it first using those 2 values. So -4 plus 0 over 2 is really like -4 over 2, or -2. Take that and sub it in to the original equation. If the -1/2 and 2 get multiplied together, then they would just make careful. Actually, I should say this is -2 that I'm subbing in. So if the -1/2 and the -2 multiply together, they make just +1. And then we multiply that with +2. And overall, that means the y value is +2. So our vertex then is -2, +2. That's going to be our starting point. Then we need to be a little bit more careful with our a value. Oops. A little bit more careful with our a value. Our a value now is -1/2. So it's telling us 2 things. The negative is telling us that it's opening down. The 1/2 part tells us what it's congruent to, or the same shape as. So it's going to have the same shape as y equals 1/2 x squared. So the basic parabola shape that's been compressed to a half of the height that it had before. Because it points down, it will have a maximum value. And that maximum value will be at its vertex, so it'll have a y value of 2. That'll be the max, and it'll occur when the x value is -2. Once again now, I want you to try and do this independently. And then, so pause the video at this stage, and then take a moment after to see how mine went, and we'll discuss it. So here are the results that I got. And I'm going to zoom in a little bit to really hammer home what's happening here. So the idea is that it is pointing down. And now take a look at how our pattern is changing. So we start from our vertex point, and then our next point, instead of going over 1 and down by 1 squared, we're going to go down by half of 1 squared. So we go down by a half a unit. Then we go over by 2, and instead of going down by 2 squared, or 4, we go down by half of that. So we go over 2 and down by 2 to end up here. And of course, we have a symmetric point over here. Then over by 3, and instead of going down by 9, which is 3 squared, we go down by half of that. So we go down by 4.5, and we end up right about here with another symmetric point here on that side. So that's how we created those points, but the overall result is that you can see we do have what looks like a more compressed shape, and that's why we use that word compression when we have an a value that's between 0 and 1, like 1/2, as we did here. So that now reviews first vertex form and then factored form, but there was a third very important form, and in some ways it's the most common form that we will see quadratic relations written in, and it's their standard form. But we've saved it till last because even though it is in some ways the most common form that you may see quadratics written in, it's the least useful for graphing. We can still graph from it, but we have to do some work on it in order to make that happen. And there's different ways we can accomplish that, but the most direct and usually the best way is to convert it using a process called completing the square that's going to allow us to put it into vertex form. So first off, just to recap, a quadratic relation in its standard form, well, we've seen equations in their standard form, so the only difference is that now we have y equals. And so that's our relation in standard form. The nice thing about it is that the a that we see in front of the x squared is the same old a value that we're used to. So one thing that standard form does tell us that's kind of useful is that the a value will let us know whether it points up or down, and how compressed or expanded the shape of the parabola is. The main problem with it, though, is that we don't know its vertex until we've converted it into vertex form. So that's why even though we know the a value, we still are going to have to complete the square and use that process that we've learned in previous situations. So let's start with this one. And this process for completing the square begins by factoring out any a value that you see. And we're going to actually just factor it out from the first two terms. So in this case, my a value is just -1. So I won't even write the one part. I'll just factor out a negative. And then I'm going to common factor that out from just the first two terms. So I create a bracket with positive x squared now and minus 4x. And then I'll just leave the -7 as a separate piece hanging off to the side. So that constant term with nothing attached, we're going to leave it out of our bracket from now and keep it aside. And now what we're going to do is take what we have inside of this bracket and introduce some extra terms to force this bracket to be something that factors as a perfect square trinomial. So in order to make it into a perfect square trinomial, what we have to do is add and subtract a special magic number. So what we're going to do is add and subtract the special magic number that is exactly half of this b value here, this number attached to your x. We're going to cut it in half and square it, and that's going to give us a special magic number. So if we cut -4 in half, we get -2, and then we square it, and we get 4. So we're going to add and subtract that special magic number inside of our bracket. And if you're forgetting why this works or how this works exactly, just take my word for it that it is going to work out well for us. So I'm going to add it and subtract it. And the reason why I'm adding it and subtracting it in that bracket is because if I do both at the same time, it's really like I've just added 0 and I haven't changed anything. But now, these first three terms form not just any old trinomial, but they form a perfect square trinomial. In other words, they factor into one single binomial that's squared. So in other words, if we write this in a bit different way, y equals negative, and then those first three can become x minus 2 squared when we factor, if we just factor the first three terms. Of course, we still have this extra minus 4 that we have to do something with. But now the minus 4, we can move it outside of the bracket. It's going to move outside of this bracket, but when we do move it outside, we have to multiply it by anything else outside the bracket with it. So it's going to multiply by a negative, and it's going to become a positive 4 outside of the bracket. So now I have something like this, and then I have a plus 4, but I still have a minus 7. And then those last two terms can just be combined together. So it's y equals negative x minus 2 squared. And then minus 3. So now it's in vertex form, and now I've got everything I need to start breaking down all of these important key characteristics. So the vertex then, we can say is positive 2 and negative 3. The entire thing must open down because it's got an a value that's negative. It's congruent to actually just the most basic parabola shape, y equals x squared. And because it points down, it has a maximum value. And the maximum value occurs when y is negative 3 at that vertex, and the x value of that vertex, oops, not negative, is positive 2. So once again, I actually am not even going to show mine in the video because you've now seen lots of examples of graphing from vertex form, and there's always a completed version of the graph in the completed version of the notes. So try this for yourself, get some practice graphing that, and then check it in the completed version of the notes that you've done it correctly. We have one other example here, and I would encourage you to just pause the video at this stage. Try going through this process yourself, and then I'm going to show you in just a moment what my steps for the completing the square were. So try this independently first, and then restart the video to see how I completed the square. Okay, so here's what I got for mine. Just a couple little tricky things about this one to make note of. And so if you maybe made a little mistake on these, don't beat yourself up because it is a common thing to watch out for. But just be careful that when we common factor out this fraction, we common factored out a 1/3. So no problems here with this becoming x squared, but be really careful with the second term. So the second term was 2x, but then when we common factor out 1/3, we have to divide 2 by the common factor. We have to divide 2 by 1/3. And that actually gives us a number larger than 2, remember? So if we take a whole number and we divide it by a fraction that's less than 1, we actually get a larger result. We get 6 in this case. So it's actually the same result as multiplying it by 3. We get 6x inside that bracket. And then, once again, we added and subtracted a magic number, which was 9 in this case. And what that 9 allowed us to do was actually take these first 3 terms and factor them into this perfect square situation. But then we, of course, still had this minus 9 inside to deal with. So notice that this minus 9, when it moved outside the bracket, had to get multiplied by 1/3. So in the next step, it didn't appear as a minus 9, it appeared as a minus 3, because that's a third of it. But then, overall, these minus 3's and plus 3's just canceled one another out, and so we actually don't see a k value at all, which really means our k value would be 0. So that's going to lead to us stating our vertex. We can say that the h part of our vertex, or the x-coordinate of our vertex, is -3, the opposite sign to what we see inside the bracket, and the k value, or the y-coordinate of the vertex, is 0. Our a value is 1/3, and importantly, it's positive, so that means it opens up, and the 1/3 part means it's going to be congruent to a simple parabola y equals 1/3 x squared. Because it opens up, it has a minimum, and that minimum y value is a y value of 0 itself, and it occurs when x is equal to -3. So once again, I'm going to end the video here, but take some time to try and plot that final one by yourself, and use the completed version of the note to check